Hello, in this video what I'm going to do is go through how to solve systems of equations by a method called elimination. So what we're going to do is start with a couple problems using substitution and then solve those same exact problems using a newer method called elimination. And then we're just going to get some practice problems and go through the scenarios of if there's parallel lines or if we have lines with the same slope and same y-intercept, and that is it. So start off with just a review of solving systems using substitution. What we would want to do is isolate one of our variables. In this case, I'm going to take this first y on top, and I'm going to isolate this value by bringing the negative 4x to the other side. And I'm going to do that by adding 4x to both sides. And that would give me y equals 4x plus 6. This is the expression then I'm going to take and substitute into the bottom equation in for y. So if I rewrite the bottom equation with my substitution, I'll have negative 5x minus the quantity 4x plus 6, and that is equal to 21. So I'm going to distribute the negative 1 through and have negative 5x minus 4x minus 6 equals 21. And then what we're doing is solving for x. So combine these like terms. Negative 5x minus 4x is negative 9x minus 6 equals 21. I can add 6 to both sides, 21 plus 6 being 27, and then that gives me an x value of negative 3. So that tells me that the x coordinate of my final answer is going to be negative 3. In order to figure out the y value, we would just substitute the x back into our original expression. So y is equal to 4 times the negative 3 plus 6. So I get negative 12 plus 6, which is negative 6. So we end up with the intersection of the two lines being the point negative 3, negative 6. So I'll do that same thing for the problem on the right. This time I think this x is the easiest variable to isolate, and I'm going to do that by adding this 2y to the other side and getting myself the expression or the equation x equals 2y plus 11. So same thing as before, I'm going to take that expression and I'm going to substitute it into my top equation for x. So if I rewrite that top equation, I will now have negative 7 times 2y plus 11 minus 2y equals negative 13. And again, distribute here. In this case, the negative 7 distributes to negative 14y minus 77 minus 2y equals negative 13. And now we're going to solve for y. So in the last problem, we started with y and we actually solved for x first. In this case, we're starting with the x being the isolated variable, so we're going to solve for y. So negative 16y minus 77 equals negative 13. That tells me negative 16y is equal to positive 64 if I add 77 to both sides. And that means y is going to come out to negative 4. So that is the y value for the intersection point of the two lines. To figure out what my x value is, I'm going to take our negative 4 and just sub it back into the equation that we had originally. So x is equal to 2 times that y value plus 11. So x is equal to negative 8 plus 11, and x is equal to 3. So that tells us that the intersection of the two lines is the point 3, negative 4. So now we're going to go through this other method, which you're going to see is a lot less work. And it really caters to when systems of equations are both written in standard form. So when, in this case, notice your variables are both on the same side of the equal sign. So these equations are in standard form. So I'm going to show you another method to obtain the same answers. So we know we're going to end up with negative 3, negative 6, and we're going to end up with positive 3, negative 4 for our answers for these problems. So what you're going to look for in these systems of equations is to have opposite coefficients. And what we mean by that is notice how this number in front of x is a negative 4 and this number in front of the x is a negative 5. So those are not opposites of each other. In this case, I have a positive 1y and a negative 1y. So that's going to be our goal, and it really is as easy as just throwing a plus sign here and combining these two equations by adding. Negative 4x plus 5x is negative 9x. If I do a positive y plus a negative y, that's going to eliminate, hence the name, and then I end up with 6 plus 21, which is 27. So right away, without even getting any variable by itself, I can get an x value of negative 3. which if I go back a slide, that was our x value. So to find our y value, we have options. I can take this x value and either substitute it into my top equation or my bottom equation, and it doesn't matter because we're really finding that intersection point, which belongs to both lines anyway. So I'm going to take, I'll just take my top equation, negative 4x plus y equals 6, and that would give me negative 12 plus y equals 6. And then if I, hold on. Sorry, that is a positive 12. So then if I subtract the 12 on both sides, I end up with 6 minus 12, which is negative 6. So we end up with that same answer as before, just doing, in my opinion, a lot less work. In this next one, if we try that right off the bat, if I do negative 7x plus x, I get negative 6x. Notice if I have a negative 2y and a negative 2y, that's negative 4y, and neither of my variables eliminated. So that's not going to be the right approach. However, if I took this top equation, and let's just say I multiplied everything by negative 1, and I'm just going to rewrite it right underneath. Negative 1 times 7x is positive 7x. Negative 1 times negative 2y is positive 2y. And then negative 1 times negative 13 is positive 13. Now I'm done with this top equation. My new system is made up of these two. Now I can add going straight down. I have an x plus a 7x, which is 8x. I have a negative 2y plus a 2y, which is going to now eliminate. And then I have 11 plus 13, which is 24. So now I end up with 8x is equal to 24, so x is equal to 3. Once again, I can substitute that value into either of my original equations. I'll just take the bottom one. So if I substitute 3 in for this x, I get 3 minus 2y is equal to 11. And I'm going to subtract 3 on both sides and get 8 on my right-hand side, which gives us a y value of negative 4. So we end up with 3, negative 4. And notice again, same answers, two different ways. And this one looks like a lot less work. So now we're just going to get some additional practice. So I have 3 more examples to go through where we're going to end up with a solution, and then we're going to go through a couple cases where we might have parallel lines, which would give us no solution, or if I have one line on top of itself, that would give us an infinite number of solutions. So these problems are a little bit different. Notice right away if I add these equations together, I don't have any variables eliminated. So we have options. Let me start over. If I want to eliminate x's, if I wanted to cancel this positive 2x, I would need a negative 2x. That means I would need to multiply my bottom equation by negative 2, and then my x's would eliminate. If I want to eliminate y's in order to cancel out this positive 3y, I would need this to be a negative 3y. So we do have options. I'll just take the first route, where we were multiplying a negative 2 across the bottom equation. And what I'm going to do is just rewrite the top equation here. So I'm not going to change anything. In my bottom equation, I'm going to multiply each of these 3 terms by negative 2. So negative 2x minus 6y is equal to negative 20. And then we now can add going straight down. So in the last 2 examples, we had eliminated the y. Now we're going to see that the x can eliminate. Negative y plus another negative 6y is a total of negative 7y, and then 6 plus negative 20 is negative 14, so my y value ends up being positive 2. Again, we have options. We can take this 2 and substitute it into either of these equations. I'll just take the top equation, so 2x minus our value of 2 is equal to 6, and then just solving for x, add 2 on both sides, and then divide by 2, and we get an x value of 4. So our answer comes out to 4, 2. And we really could have done this same problem using substitution, which I'll just show you real quick, and you do not have to take this down on any notes. But if I wanted to solve the system using substitution, I could take this x and get it by itself by subtracting 3y on both sides. And what I would do is then take that x value, negative 3y plus 10, substitute it into my original equation, and then we would end up solving for y. And again, we would get the same answers. It just ends up being a little bit more work, and that really comes down to the forms of equations that we started with. So in this case, we started with equations in standard form, and we can really focus on coefficients, meaning again those numbers in front of the variables, and see if we can determine opposites. in this case, it's going to be easier to eliminate x. I can see right away. If I want to cancel out a positive 4x, I would need this bottom to be a negative 4x. Not as easy on this right-hand side. Notice there's not a nice number I can multiply 5 by to get to 7. So what we would actually have to do is multiply both equations if I wanted to eliminate y's. I'll take a hard pass on that, and we're going to go ahead and just multiply the bottom equation by negative 2. Again, I'm going to rewrite the top equation over here without changing a darn thing. And then I'm going to rewrite this bottom equation now after I distribute negative 2. Negative 2 times 2x is negative 4x. Negative 2 times 7y is negative 14y. And then negative 2 times negative 23 is going to give us a positive 46. So now I'm going to add, going straight down. Notice my x's will eliminate. And that only occurs because I have the opposite lead coefficients, meaning I have a positive 4 and then a negative 4. So since they're opposites, they'll cancel. The negative 5 plus a negative 14y gives us negative 19y. And then 49 plus the 46 is going to give me 95. So dividing both sides by negative 19 gives me a y value of negative 5. And we can take that and substitute it into whichever equation we want. I'm going to just choose the bottom equation and rewrite that bottom equation, but now I'm going to take negative 5 and substitute in for y. So I'll end up with 2x minus 35 is equal to negative 23. If I add 35 to both sides, I end up with 2x is equal to positive 12, and then x comes out to 6. So our final answer written as a coordinate is the point 6, negative 5. Which takes us back to the original point of why are we doing this. This is finding the intersection of both lines. How exciting. Okay, maybe not. Alright, and then lastly, an example where we do have to multiply both equations. And once again, just to make this video longer than it has to be, I'm going to show you both ways. So, total preference. In the first way that I do this, I'm going to eliminate x's, and then I'll do it again and I'll eliminate y's. And I'll at least just do the first steps, save a little bit of time. So if I want to eliminate x, think about what the least common multiple of these numbers is. And when I say least common multiple, that would be like you counting by 4s and then counting by 3s and see what's the least number on that list. So if I count by 4s, it's 4, 8, 12, 16, blah, 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 blah. And if I count by 3s, it's 3, 6, 9, 12, and blah, 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 blah. I can already see 12 is my least common multiple. So what we think about is what would I need to multiply the 4 by to get to 12, and that ends up being 3. And then what would I need to multiply 3 by to get to 12, and that would give us 4. Here's the problem. If I take 3 times the 4x, I'm going to end up with 12x. If I do 4 times the 3x, I'll still get a positive 12x. And when I add these together, they don't eliminate. So what I need to do is pick one of these values for a multiplier and just tack a negative on there. And I'm just going to, since I did it on the 4, I'm going to leave it on the 4. So I'm going to rewrite now my top equation, 3 times the 4x, which is 12x, 3 times the negative 5y is negative 15y, and then I have 3 times the 6, which is 18. Bottom equation, negative 4 times 3x is negative 12x, negative 4 times 2y is negative 8y, and then I have negative 4 times 16, which is negative 64. Now I end up with both equations. In this case, my x's are going to be eliminate. The variable to eliminate, negative 15y plus a negative 8y is negative 23y. And then on this right-hand side, I've got negative 18 plus 64, which is going to give us negative 46. Cool. And then y ends up being a value of 2. Now I'm going to just do it the other way, where I'm going to show you over here, because what I would do again from this point is take the 2, substitute it back in, and figure out my x-coordinate. But I'm going to do this another way, where I'm going to go back from the original equation, and let's say I wanted to eliminate y's. So think about my least common multiple between 5 and 2, which ends up being 10. We already notice in this case this top equation has a negative 5y and the bottom has a positive 2y. What that means, since my signs are already opposites, is I can just multiply the top equation by positive 2 and the bottom equation by a positive 5, and our y's will eliminate. So my top equation would be 8x minus 10y equals 12. My bottom equation is 15x plus 10y, and that one's going to equal 80. Now I end up with 23x. Y's eliminate, and that is going to give us a value of 92, and x comes out to 4. So what I would do again, just to verify that this actually worked, if I take 4, I'm going to substitute it back into my top equation. 4 times 4 minus 5y equals 6. I get 16 minus 5y is equal to 6. That means if I subtract 16 on both sides, I would get negative 10 on the right side. And then y ends up being 2, which, hey, that was our answer the first time we did it. So our final answer for this problem then ends up being the 0.42. You do not have to do all this work on the right. If you were totally cool with the first side of me doing this, solving for y, again, I can just take this value of 2, substitute it back in for one of your equations, and solve for x. I just chose to show you that, hey, we could have eliminated x or y first. So then, we end up with the last case. What if I've got no solution or an infinite number of solutions? So what we'll notice in this first system is if I want to eliminate my x's, I can just multiply my bottom equation by positive 2. And I would have a positive 2 on top, negative 2x on the bottom. Those will eliminate. So again, I'm going to rewrite my top equation without changing anything. And now I'm going to multiply my bottom equation by positive 2. And that would give me negative 2x plus 4y equals, and then that is negative 8. If I add going straight down, notice that both of my variables drop out. Right away, that tells us we're going to end up with 0 on the left, and that tells us we're either going to have a no solution or an infinite number of solutions. The fact that we get a false statement here, I get 0 equals 2. The fact that that is not true tells us that we have no solution. And what that means is if I were to write both of these equations in slope-intercept form and then graph them, you would end up with two lines that would have the same slope in different y-intercepts, meaning parallel lines. It's going to be a little bit different of a case for part B. In part B, I'm going to end up multiplying both equations. I can see that there's not a nice number I can multiply 2 by to get to 3. There's nothing nice to multiply 6 by to get to 9. So what I'm going to do is eliminate my x's. And I think about a least common multiple that 2 and 3 both go into, which is 6. If I multiply my top equation by 2, I'll get to 6x. And if I multiply my bottom equation by 3, I'll get to negative 6x. So my top equation, I end up with 6x minus 18y equals 30. And then my bottom equation, I get negative 6x plus 18y, and that's going to be negative 30. So now watch what happens. When I add these going straight down, I get 0 on my left, which again tells us we're either going to have no solution or an infinite number of solutions. The fact that I have a 30 plus a negative 30 and that comes out to 0, I get this true statement here. And that's an infinitely many solutions problem. And what that means is that these equations are technically the same line. So if I were to graph this, you would end up with one line right on top of itself, which means that they are always crisscrossing at every single point. So there's an infinite number of solutions. So just to kind of recap, going back to the top, we solved these systems at the very beginning using substitution. And since both equations were in standard form, it was probably not the best or preferred method. It was a little bit more work because notice the first step that I did in blue in each of these problems was to isolate a variable. And that's not always going to even be as easy as this problem was. So then we kind of analyzed, okay, it was a lot easier to solve those two systems using elimination. Went through 3 examples where you had to either multiply one or both equations in order to cancel out one of your variables. And then we finished up looking at systems of equations where your variables both eliminated, which gave us either no solution or an infinite number of solutions.